Welcome, as always, to this little corner of the multiverse. I hope you enjoy this corner. It's got a lot of chemistry. It's got a lot of green. What else could you possibly want other than maybe some mathemagics? And we got that coming. So you are in the right place. Okay, today, one topic, calorimetry. Boom. Well, that might lead to the question, what is calorimetry? Well, it's the study of heat flow, which is really what we've been doing, but more specifically using a calorimeter. Well, what is a calorimeter, you might ask? And I'd say, excellent question. Sort of. It's really just any device used to measure temperature. So this is a calorimeter, if I stick a thermometer in it. Although that would ruin the coffee, so I'm not going to do that because I like my coffee. But really anything can be a calorimeter. There are two standard versions of this. One is a coffee cup calorimeter, which is literally go over to 7-Eleven, buy one of those big styrofoam cups, jam a thermometer through the top, use your hand to gently and consistently stir it, and congratulations, you have made a calorimeter. So what's the what would that be made of? What would be, so let's go back to this idea of system and surroundings. What would be the system here? Well, the system, you could say, is the solution where the chemicals are reacting in, the thermometer, the air, the coffee cup. I mean, it could be your hand, it could be the surrounding area, it could be the table it's on. But I'm just going to use these couple things. You get the idea. It's maybe a bunch of things. So let's look at this more specifically. If we want to look at that change from the chemical reaction, and some of you at home are probably wincing, so let me put the negative sign in there, that the flow of energy has to be equal and opposite, so that's a negative sign. But that change, that energy change is really what? For the calorimeter, it's made up of the thermometer, the air, the coffee cup, the solution, my hand, the table, etc., etc., etc. And all those things, even no matter how much, you can break them down more if you would like, but all of those things are made of consistent chemicals that we could call substances that have an individual Cm delta T. So there's a Cm delta T associated with thermometer, thermometer, thermometer. Air, air, air. Coffee cup, coffee cup, coffee cup. Solution, solution, solution. Hand, 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 etc., etc. You get the idea. I just want to lay out the principle here. The change in temperature, all these things are touching at the beginning. If they're touching, they have the same temperature. They're all touching at the end, which means they have the same temperature. So delta T for all of these are identical, so you can factor it out. Now, if we assume that we take this fancy apparatus, again, coffee cup, thermometer, boom, hand in the middle. We take our fancy, super fancy duded setup and do it the same way every time. And what's true? Same thermometer, same mass, same air, same hand, same coffee cup, same solution, same stirring practice. All of this becomes what? A constant. So if we're given setup, this is all a constant. We might even call it a calorimeter constant, or heat capacity if you want to be more specific and consistent with what we've been doing already. But this really boils down to Q of our calorimeter. So we're finally to the Q of the object. I know I've teased it for a couple of videos, but we're finally at Q of the object. And Q of the object, or calorimeter, is going to be big C times delta T. Good news is math is easy. You might say, Dr. Wergo, I know you're mocking this whole thing with the coffee cup and just jam a thermometer through. What would a real setup look like? Okay. So it's a bomb calorimeter. Oh, no, not that kind of bomb, sorry. Might have been before we had good equipment, but now it's safe. So they take a very small reinforced vessel, they jam like 10 atmospheres of oxygen in. You can imagine if manufacturing was terrible, say in the, well, I shouldn't say terrible, not up to snuff in, say, the late 19th century. These things might occasionally depressurize and blow up, hence the bomb calorimeter idea. We have that in there. We put it in another reinforced tank. See, again, we're being safe. Filled with water, thermometer, stir bar, maybe some some wires and a little coil and a little pan down here. We take some dry food down there, put it on there, hit the button, and we burn it super fast in our super oxygen. Changes the temperature here. We record that, and we can get the calories in your food, believe it or not. That is the classic way of doing it. They do more biomedical analysis now where they actually don't look at the calorie content, they look at the biological activity of the calorie content. But anyway, this would be your traditional way of looking at the calorie content, and certainly the energy in your food, whether you absorb all of it or not, is another argument to be had for another day. I'll say that for your nutrition classes. Okay, I promise mathematics and I deliver. All right, here we go. When 23.6 grams of calcium chloride is dissolved in a coffee cup calorimeter, the temperature of the water increased from 25 to 38.7 degrees Celsius. If the heat capacity of the calorimeter is 1,258 joules per degree Celsius, what is the molar enthalpy change for the reaction? Holy smokes, there's a lot of words up there. It's okay, because we notice a couple things. I notice there's a change in temperature. That means I'm doing a Q problem. Next thing is, how many Qs? Well, we got this is dissolved, causing a temperature change. So that's really the chemicals changing from a solid to individual aqueous ions. That sounds a lot like a chemical reaction. We got the calorimeter itself. That sounds like a thing. And if you got calorimeters, at least 2 Qs, just for the record. We got the calorimeter. And then, let's see, calorimeter, reaction. And that's all I see. I just see the words calorimeter, I see the words reaction, I got 2 Qs. So I'm going to set that equal to 0. I might even make this a little bit. I like to distribute that idea that the heat flow is equal and opposite. Equal, but opposite inside. One's gaining, one's losing the same amount. So there we go. So a chemical reaction. Is that most like a pure substance, an object such as a calorimeter, or a chemical reaction? It's a chemical reaction. Very good. And delta H. Fantastic. A calorimeter. Is that a pure substance? Is that an object like a calorimeter? Or is that a chemical reaction? Probably calorimeter. So I'll put calorimeter there. Awesome. Guess what? The rest of this is just the math. We just got to solve for molar enthalpy change. So remember, enthalpy is H, change is delta. Molar means per mole. That's just telling you your units. And it's molar enthalpy change will always be molar in our class. So we're looking for delta H. So I'm just going to move this over. And boy, can't get much simpler than that. That big C is given to me. Fantastical. My temperature change. Now we got to make sure we go in the right direction. From here to this, so it's 38.7 minus 25. And then N is moles. So we do have to solve for moles. So we have 23.6 grams of calcium chloride. You divide by the formula weight. I get 75.45 grams per mole. Please note, even on this problem with one chemical, I'm still putting in my labels. Get in the habit. If I can write those labels every time, so can you. I see you. I see you right there. I see you rolling your eyes. I see you making faces at me. Do it anyways. Oh, and by the way, make faces at me all the time. Print out my picture. Throw darts at it. I don't care. But in class, when you're working problems, happy, positive place. That's what chemistry is. And it'll give you a growth mindset, and you'll do better in your classes too. Believe it or not. I mean, it's mind over matter. It sounds hokey. It is hokey. But it works. .313 moles. And the rest of this is just plugging and chugging. And I get, for my answer, negative 55,000 joules per mole. That's huge. I don't know what 55,000 looks like, but I know what 55 looks like, so let's convert that. So that's going to be negative 55 kilojoules per mole. Then it looks standard. We look like a chemist. And again, who wouldn't want to look like a chemist? I mean, really. And that's pretty much it for the math. So this is easy. I hope this is easy. It seemed intimidating, but boy, that didn't seem so bad. So again, if you're thinking, boy, that seems too easy, I wonder if there's other ways to do such a problem. The answer is yes, there are other ways to do this. I'm not going to work every single problem, but I do want to point out a couple other common wordings you might see. Sometimes they make it a calorimetry problem, but it's not a calorimetry problem. Like it'll say, in a coffee cup calorimeter, 100 milliliters of water is combined with 23.6 grams of calcium chloride, the temperature changes, blah, blah, blah. And then at the end, they go and they ruin it by saying the heat capacity of the solution is the same as water, and the calorimeter is an isolated system. Or they might say the heat capacity of the solution is the same as water, and no heat is lost to the surroundings. Or they might say the heat capacity of the solution is the same as water, and assume that the solution absorbs all the heat, or there's a perfect heat transfer between the within the solution. So again, verbiage changes, different ways of writing this. What they're trying to tell you is you don't actually have a calorimeter. It's just the water and the chemicals. So if you're doing something like this, now it's going to be the chemical reaction plus the change of the solution and not the calorimeter. And now the solution is supposed to be dealt with as a chemical because it's saying treat the solution as you would water. So anywhere where you see treat the solution as having the same capacity as water, that's going to be a Cm delta T giveaway. So in this case, it would be N delta H equals negative Cn delta T. And just remember, the mass is the solution, so it's the solute plus the solvent. So we have to do the 100 grams of water plus the 23.6 grams of calcium chloride for 123.6 as our total mass. Otherwise, the mechanics of this problem will be the same. Heat capacity of water still 4.184. Still another version of the same problem. Chemical stuff, blah, 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 is done in a bomb calorimeter. They give you a capacity. And the bomb calorimeter contains water with a capacity. So they're trying to tell you here something, because sometimes you don't always fill out the bomb calorimeter exactly the same each time. So they're saying, this is a practical, this comes out of lab. This is a practical thing where you would weigh the water each time and do that as a separate calculation. And if that's the case, they're really saying there's 3 Qs. I do like this as a test problem because I can ask one question and get all of the Q stuff done in one problem and see if you can do it. So we get Q of the reaction plus the calorimeter, and it's telling you treat the water separately if you see this type of wording. So now it's N delta H equals, and I move these over to the other side, minus C delta T for the calorimeter, and that the C is given to us. And the change in temperature is going to be the same for both pieces of the calorimeter, the water and the calorimeter itself. And then minus Cm delta T for water. So this is still 4.184. This 1.2 liters would be 1.2 kilograms or 1,200 grams. That would be our mass, and our change in temperature is identical for both. So those are the other versions of this you'll see. We'll work some in class with the learning catalytics. But I did want to just point out that the wording can change a little bit. It fluctuates. Everybody seems to write their calorimetry problems just a smidge different. And that's that. Thank you so much for your time. Have a wonderful day. And yeah, it's beautiful outside. Hope it's beautiful outside right now through the space-time continuum. And enjoy it. If not, if it's rainy, stay inside, work chemistry. It's an awesome excuse. Man, I would love to go out and do something with you, but I got to do chemistry because it's raining.